All right, everybody. Hello and welcome to the Columbia Memorial Space Center for this month's edition of Space Center Live. So glad to have you all here with us, just making sure our stream is up and working. And we've got a really fun one for you here today, where we're going to be talking about rockets, probably one of my favorite things. And speaking of me, I'm Jared Head. I'm one of the activity specialists here at the Columbia Memorial Space Center. So aerospace is kind of my bag, and rockets are definitely right up there with it. So if you have any questions, just to kind of give you a little rundown about how we do Space Center Live here, we are doing a little talk to kind of inform you, but at the same time, I do have access to the chat with you there. So if you are inquisitive, if you got any questions or anything, let me know, and we will throw it in and check that out and make sure that your questions do get answered today, because that's ultimately what we want to do. We want to get you here and watching us and learning a bit, and we have got quite a bit to go over today, because rockets, believe it or not, bit complicated, just a bit complicated. So we're going to go ahead and get started with our presentation that we have ready to go for all of you here today. So one of the cool things about all of this is that there was a lot of research to be done, and including myself. So just because you think you know a lot doesn't mean you know everything. And this was a really fun one, because I got to learn a lot in building this talk. So hopefully you all get to learn just as much as I did with that there. So without further ado, as we show off the magic that makes it happen right there, a brief history of rocketry happening today on July 2nd at 2 p.m. Pacific Daylight Time. So as we said, of course, once again, very glad to have you all here with us today. So kind of what we're going to do with this here is we are going to talk about the history of rocketry a little bit. We're going to talk about how rockets work, and then we're also going to talk about current rockets and future rockets that are coming up as well. And as I mentioned earlier, if you have a question, feel free to throw it into the chat room. I have access to the chat room, so we could definitely talk to you directly. And that's kind of half of the fun of working the Space Center Live, is because we're talking to you and we want you to talk back to us. So if we want to talk about rocketry, we've got to go very far back. So lots of people think that rocketry is something that is brand new, that it's just recently kind of cropped up in the past 50, 60 years, something like that. But actually it isn't. You can go back nearly over 1,000 years, it turns out, a millennia, to some of the first rockets in the Hulangjing, which was a Chinese book that was written in 1380, sort of a how to do war book. There was a mention of a device called a Hojian, and that translates roughly to fire arrow. And the Hulangjing puts this, it's sometime between 969 and 1000 AD when this was invented. In that book itself, there is no real definitive time. So based upon just learning and understanding the history of dynasties in China, historians have been able to kind of narrow it into that 31 year time frame as to when it happened. And then the world started to catch up at that point. So Mongolia was really one of the first that was using rockets effectively in war, in battle, when they were traversing across Asia and conquering and capturing everywhere. Those rockets from Mongolia eventually made their way to Europe in the late 1200s, where they really, I don't want to necessarily say didn't do much with them, but they just weren't as on the front of warfare and other things like that as, say, in China or Korea or Mongolia at that time. The same with the Middle East as well. The rockets came in about the late 1200s. India actually independently developed their own rockets in the early 1300s, and they were using them for war pretty consistently. And then Korea as well in the late 1300s developed their own rockets and, in fact, their own rocket weaponry as well. This is in a history book from China back in the 1500s. This is actually a Chinese diagram of a Korean weapon of war that used rockets called the Hachwa. And if you've ever seen Mythbusters, you know they did an episode where they actually tried to see if it would work. So basically what this is that you've got these little tubes, like 100, 150, 200 little tubes that are on a cart. So you can wheel this cart around. And in those tubes, you put your little rockets, and you will put the fuses out the back of these tubes, and you'll light the fuses individually as you go through all of these. So you'll be launching a lot of rockets over a very long period of time to do that. And at least in terms of the history that's been written down about early rockets in this time period for warfare, they weren't particularly effective. It was more a psychological weapon as opposed to an actual, like, blasting a group of 100 people all at once kind of weapon. So rockets back in that time, certainly not rockets like we have today in terms of their use in warfare. Now, if we want to start sort of getting into the modern rockets that we work with today, we do jump a little forward and we go back to Europe in the mid 1500s. There was a actual engineer by the name of Conrad Haas in the Transylvania area who ended up writing several books in terms of metallurgy and alchemy, at that time, talking about ideas in how to improve these rockets. He ended up working with things like mixtures of gunpowder. He actually also started to propose things that we would call very similar to our modern rockets. He proposed the idea of having multiple stages in your rocket, which is critical to allowing your rocket to actually reach space. He proposed the idea of liquid fuel, so finding two liquids that you could mix together and make that happen. He also proposed ideas like the shape of wings, like delta wings. If you're wondering what a delta wing is, think about the space shuttle. Most of the time when we think of the wing of an airplane, we think about sort of like a strip kind of coming off of that there. But in the case of a delta wing, it's literally, put the body of your vehicle in the middle and then sort of put a triangle on the side of it. And that's what it would be. There were even nozzle designs that were very similar to what we use today. So Conrad Haas showing off a very good understanding of physics with that there. And Rick O'Connor saying, so rockets have always been a lot of effort. Yeah, it turns out, I guess they always have been quite a lot of effort for it there. And in fact, some dynasties and emperors during the time period when rockets were coming up literally did basically say, this is too much effort, we're not going to use it. So I guess trade-offs with that there. So now this next one I want to talk about is just a little bit of a footnote in history. And Rick, you're asking, is that where the Delta rocket gets its name? That's actually a really good question on that there. I guess we get the first one to stump me today. So I actually don't know where the Delta rocket gets its name from. That's a very good one. For those of you who are wondering, the Delta rocket was a rocket derived from Thor ICBMs, and it flew essentially from the late 50s all the way until 2018 with its final launch as a Delta II rocket. So they did upgrade it consistently throughout its time when it was being used. But actually, I legitimately don't know why they called it that. If anybody's on Twitter, you can definitely hit up the company that operated those, United Launch Alliance. Their handle is @ULA Launch. Or you can even hit up the CEO of United Launch Alliance, Tori Bruno, @Tori Bruno on Twitter. They're usually very responsive as to why if you ask a question, they'll get you an answer or try to find you an answer if they could tell you at least. So that might be a good one to go ahead and fling at them. So if somebody watching wants to ping them real quick, who knows, we might get an answer by the time that we're done with this here today. So kind of just want to talk a little bit about this one, more like a little note in history with this here. Lagari Hassan Salibi, who was a Ottoman engineer, was reported to have actually made the first crewed flight of a rocket. He essentially strapped rockets to a chair, and he had about 140 pounds of gunpowder. He did it over in the Bay in Istanbul, and was apparently successful enough that he launched himself into the Bay. Before he launched himself, as he was setting himself up on here, with royalty watching him, as he was going to do this, he said to them, I'm going to be going to the sky, and I will talk to God on your behalf. And when I return, I will give you the answers that he gives me. But obviously, he did not fly very far, if the story's true, and splashed down in the bay in Istanbul. And as he was swimming the shore, he was reported to have said, God gives his regards, as sort of a joke with that there. But I thought that was a very interesting moment, strapping rockets to your chair and launching yourself. I don't know if I would do that. But yeah, that's if true, if completely verified, then that would be a very interesting note in history for the first crewed rocket-powered flight. Then we go on to India. Like I said, India sort of became the central area of development, returning rockets as a weapon of war. The reason India came onto the forefront of that was because we were no longer making rockets out of materials that could be found on the ground. India switched over and started making rockets that were made out of metal materials, such as iron. And these rockets were significantly stronger than what you could launch with previous materials. These rockets were also capable of flying miles at a time. So these were a devastating weapon of war, and actually helped defeat the British in the late 1700s, when skirmishes were occurring at that time. And in fact, the British brought rockets back with them. And a gentleman by the name of William Congreve was the sort of next step in rocketry, where he figured out how not just to make rockets out of metal, but also to enhance rockets. What can we do using physics to kind of enable rockets to fly further, fly more precisely? How do we make these rockets bigger so we can carry more gunpowder or explosive when it lands, so we can increase the effectiveness of a rocket as a weapon of war? So some of the things that he did, he figured out, is that you can obviously stuff more than one rocket in the same body. So sort of a very rudimentary multi-stage rocket. So having more than one rocket, once your first rocket's done, it drops off, the second rocket ignites, but very rudimentary, not very reliable on what he was able to do. Also stabilizing rockets as well. They ended up figuring out that much like a bullet from a gun, if you can get it to spiral, you can get it to actually fly very nice and straight. So that was something that they were able to do. Now, this is where we really start to get into rocketry as a normal, average, everyday person would start to expect it. And that is with the modern father of rocketry, if you will. Someone that if you wanted to point to, you could point to this person and say that this person is the reason that rocketry is how it is and helped us figure out how to make rocketry work. And that's Konstantin Tsiolkovsky. And Tsiolkovsky worked in the early 1900s in Russia at that time. And he was really one of the first people to apply serious mathematics. So things like algebra and calculus and other things that really started to nail down the physics of what makes a rocket work and how to enable that and how to enhance that and what you need to do to make that happen. He came up with something that we now call the rocket equation. This is basically a way to derive just how much energy you are going to need for your rocket to lift a certain weight. And we end up calling it the tyranny of the rocket equation as well. And that's because the more you want to carry into space, the more fuel you have to carry. So another way to explain this, the tyranny of the rocket equation, is that when you are adding more weight on, you add more fuel. So let's say I want to carry a pound to orbit. Okay, so I have to carry this much fuel. Okay, I want to carry 10 pounds to orbit. Okay, so I have to carry fuel, and then I have to carry the fuel to make sure that I can carry my fuel and my 10 pounds to orbit. All right, let's step it up to 100 pounds. All right, I'm going to need to add fuel to carry the fuel, to carry more fuel, to carry the fuel to get my 100 pounds to orbit. So when you graph it out, when you actually put it on a graph, you end up seeing that you get an exponential chart. So let's imagine, in front of me over here, in my little Zoom window over here, that we have a chart, and our x-axis right here in front of me, side to side, that is the amount of energy that we need to put something into orbit. And then my y-axis over here, up and down, that's how much weight. So the further we go up, the more weight we're going to want to carry. Well, if we graph it out, it looks a little something like this. So you have that nice steady line and then a very sharp curve. So it's exponential. So it actually increases, and that increase will increase the closer you get towards more weight. So that's physics. That's just the way it works. And that's one of our big problems in rocketry, which is that if you want to carry the fuel, you have to carry fuel to carry the fuel, to carry that fuel, to carry the fuel, to carry the fuel, to carry the fuel, to get your payload where it needs to be with the fuel it needs to be. So with Tsiolkovsky's work, we consider him sort of the first true astronautical engineer. He sort of put research into actual space flight, and some of his books actually do propose things such as interstellar travel, even intergalactic travel on massive, what you could call generation ships. So imagine carrying tens of thousands, hundreds of thousands of people. He was already thinking about this in the opening decades of the 1900s. So one of the most important, if not the most important, of those who started rocketry. Then we move on to Robert Pelletre, who was a French engineer. He ended up calculating the energies that were needed in order to make spaceflight work, and he also derived the mathematics for spaceflight as well. So basically figuring out the physics, really narrowing down what this is going to take with all of that. And he actually did something very interesting at his time in the early 1900s because radiation was something that was brand new, that was being found. He actually did some work, some calculations in physics to try to figure out if you could harness this newfound idea of the nuclear world as a rocket. And he actually did propose, and I had some ideas of nuclear rockets back in the 1910s. So now we're beginning to, in present day, 2021, we're beginning to have a revival of the idea of developing nuclear-powered rockets, essentially systems that use a nuclear reactor to heat up their fuel. They don't spit radiation out. They just use a nuclear reactor to work with the fuel to heat it up and get it ready for use to make it more efficient. But he was thinking about that 110 years ago. So, these people, I know a lot of people say we're really smart nowadays, but back then people were really smart too. And even going all the way back to developing these rockets, kind of how it goes with that there. If you're in the United States, like we are, you're a big rocket person, you probably recognize this one, which is Robert Goddard, considered sort of the American father of rocketry and astronautical engineering. He worked in the early 1900s, and he actually ended up working all the way through World War II until his passing in 1945. He actually did not start out in rocketry. He had rocketry sort of as like his secret hobby. Don't tell anybody that I've read all these H.G. Wells novels and I want to make the space ones happen. But he was really actually motivated by that in order to make it happen. A lot of modern rocket design, the ideas in it, you'll find it in his initial ideas. And those modern designs include things like liquid fuels, control systems, even structural design to make sure that your rocket stays with it. And really the difference between him and many other people is that he went and got the money to actually go out and fly these ideas. He built prototypes. And in addition, he also published his results publicly, which in doing so actually made him a bit ostracized. A lot of physicists looked at him and basically said, if space is a vacuum, then how's anything going to work in it? Well, it turns out that these people were definitely forgetting about Newton's laws of motions, such as a object will move until a force acts upon it. I would have thought people would have thought of this back then, but apparently the naysayers just really weren't paying attention to people like Isaac, like Newton's laws of motion, which you think would be important, but but he did. I don't want to necessarily say he was outcast from the scientific community, but he took a lot of flack. But the thing about Goddard is that he stood his ground with what he did, and much like Tsiolkovsky from earlier, Goddard was a bit of a recluse, not as reclusive as Tsiolkovsky was basically doing all these equations by candlelight in a cabin in the middle of the forests of Russia. Goddard was just more sort of not out and about throwing everything out in front of everybody like a showman, but he's still by most standards considered reclusive and not really opening up, even though he published his results publicly. And of course, we hearken to this famous photo of him standing next to one of his designs. You can actually see that the liquid fuel tank down at the bottom of the rocket there, and the fuel lines leading up to the nozzle, which is where the fuel comes together and ignites at the top of the rocket. So these ideas a little backwards to how we do it nowadays, but definitely sort of putting in a good effort to think about the physics of what it is with that there. Then Herman Ober comes in the 1920s in Germany. He was really one of the first to calculate multi-stage rocketry, which we now know is how one of the primary ways that we overcome the tyranny of Tsiolkovsky's rocket equation. Remember that exponential gain in energy you need? Well, one of the ways we figure that out is that we drop parts of our rocket that we don't need anymore. So he was sort of one of the folks that helped calculate that very precisely what that's going to look like. He also helped develop astrodynamics. This is the idea of trajectories and motion in space and how your vehicle firing its engine a certain direction for a certain amount of time for a certain amount of energy will affect its orbit and other things like that. And in fact, he actually figured out a maneuver that we named after him called the Oberth maneuver, which is basically going in close to an object with gravity and firing your engine as you're close to it. And normally, you would fire your engine at the highest point of your orbit, so that way you circularize it. But if you really wanted to build up some tremendous speed to go somewhere, say like a mission to fire a probe out of the solar system as fast as possible, you would do what we call an Oberth maneuver. So you would basically probably fly that probe as close to the sun as we can engineer a probe to do, and then when it's at the sun, at its closest, fire that engine and just speed up as fast as possible out of the way there. And the amazing thing about Herman Ober working in Germany at that time, he was actually Werner von Braun's engineering mentor, which is just fascinating to think about. And then, of course, we have to come to the man I just mentioned, Werner von Braun, which his work started in the 1920s as he was learning under Herman Ober there. And actually, Ober ended up working for von Braun when von Braun and his team was brought to the United States. But he was his primary work was done in 1940s Nazi Germany. And I mean, no way of getting around it. He worked on a weapon of war that was a weapon of mass destruction that killed thousands of people in its use, and also tens of thousands of people in its manufacturing. So no reason to sugarcoat history. He developed this rocket technology that he developed was done for the Nazis. And eventually, at the end of World War II, he surrendered to the United States with his team. And the United States basically said to him, you can go to Nuremberg and hang with some friends, or you could come to the United States and develop rockets for us. And von Braun decided to come to the United States and build rockets for the Americans. So those early rockets that you see, such as the Redstone rockets, which was used to launch the first couple of Mercury capsules on suborbital flights, and then finally the Saturn rockets, which are still Saturn V, still one of the biggest rocket to ever successfully fly on missions and into orbit. All the brainchild of his work that he did there, and he worked from 1940s in the United States to the 1970s. If you ever read the book, The Right Stuff, there's quite a lot that talks about Werner von Braun and some of the clashes that he had with the U.S. military military. He also really wanted to popularize the idea of space flight, so he became very good friends with Walt Disney, and ended up doing several specials with him on Walt Disney's TV show talking about space flight. So if you've ever wondered why Disney was so interested in space flight, Werner von Braun was actually the reason for that there. However, over in the Soviet Union, that does not mean that they weren't up to anything at that time. They most certainly did capture German scientists as well. But the thing about the Soviet Union is that their ace up their sleeve is that they already had their own equivalent of Werner von Braun in their country, which was Sergei Korolev. He worked from the 1940s to the 1960s. He has a very interesting story, which he was working as an engineer developing rocket technology. And his primary rival, Valentin Glushko, basically said that Korolev was not good for that, and he should be sent to the gulags. And he did end up actually being sent to a work camp, a gulag in Soviet Russia. And he was only pulled out of it to develop his rocket technology. But once he was pulled out of it, he sort of got his revenge on Glushko because he ended up taking over Glushko's work and developing some of the Soviet Union's and really some of the world's first intercontinental ballistic missiles. And a bit of luck happened with the Soviet Union in why they were able to get the first satellite into orbit and the first human into orbit as well. And that's because there were differences between the nuclear warheads that the United States and the Soviet Union had developed. The United States nuclear warheads were incredibly sophisticated, technical marvels of that time, and they were not particularly big. There was an emphasis on small nuclear warheads. So the rockets that the United States had at that time, the intercontinental ballistic missiles, were not very big. However, on the other side of that, the Soviet Union had very crude, very rudimentary nuclear warheads. These were big, they were heavy, and you have to have a big, gigantic rocket in order to do that. And if you have a big, gigantic rocket and you put something that's maybe 10, 20 pounds, maybe 100 pounds on it, when usually you're carrying like 5,000, 6,000 pounds, you could probably put that in orbit. And that's basically what the Soviet Union realized. They realized that they could take one of their best and heaviest lifting intercontinental ballistic missiles, the R-7, and launch Sputnik atop of it. And then eventually modify that as well, and then launch Vostok 1 with Yuri Gagarin on it as well. And in fact, the R-7 intercontinental ballistic missile eventually became the Soyuz rocket, which is still used today by Russia to launch astronauts and payload and satellites to space. So Sergei Korolev's designs were so good that they're still operating today. And Korolev really kind of ran the Soviet space program in the opening decade of it there. He was definitely on par with von Braun in terms of ability and other things like that. But Sergei Korolev did not live, unfortunately, did not live long enough to kind of get the Soviets on a moon program. He died in 1966. And Valentin Glushko, his rival, who very often did not see on the same eye, was the one who came in and basically said, I'm now in charge. And because of this, I'm going to dismantle everything that Korolev did, which was a very bad idea. So if you've ever wondered why the Soviets really never ended up doing a lunar program, they were on their way. They really did actually want to do one, regardless of whether they were going to be first or second. But the thing was, once Korolev died, the motivation was gone, and then his rival Glushko came in and basically said, me and him didn't like each other, so I'm going to get rid of what he did. So that's kind of the end of the moon program for the Soviets, and then they switched over to space stations instead and were excellent at building space stations. And then finally, once we get to the 1970s, we're no longer looking at individuals kind of running how things work. We're looking at a team. So there are now essentially specializations for people, such as myself. I do primarily propulsion and operations work and other things like that. So that engineering team is kind of how it goes now. It's really difficult to like point at one single person and do things, even at a place like SpaceX that does have someone as prominent as Elon Musk in their top position, if you will. There's still, I can guarantee you, there's still a lot of teamwork that's still happening there to make sure that those things are going on. So Don't forget, it is a team effort. A lot of people have to work together to make things happen. It's not just one person that spearheads anything. It definitely helps to have a highly motivated person at the front to spearhead things, which is good for certain companies and the way they operate, like SpaceX. But nowadays, it is a team effort. There's no real single person that checks off on everything and says this is the way it's going to be. So now that we've talked a little bit about the history of rockets, I want to talk about the 4 basic principles of rocket engines. A lot of people think rocket engines and rocket science is particularly complicated, and it is. There's a lot of math involved, as you can imagine. There's also a lot of nowadays coding and simulation work and other things like that go into it and are involved with it. But there are 4 basic principles of rocketry. And of course, just I'll let everybody know, since we're kind of coming on the halfway point, if you have any questions at any point, feel free to throw them into the chat. Space Center Live, we're interactive here. I can see the chat room. So if you have any questions, ask them. I'll answer them. We've already had one question today, which stumped me. So which is, do that. I love it when that happens, because then I get to go learn as well with that. So if you have any questions at any point, just drop them into the chat, and we're happy to answer them for you. Or if you're watching this on demand, I'm very sorry. Catch us at the next Space Center Live with that there. So what are the 4 basic principles for rocket engines? Well, if you follow these 4 basic principles, you can never go wrong. And I have to say, these 4 basic principles are not my own doing. They are from a friend of mine, but they are very good. So I feel like it's a good intro for people who typically don't really think about deep engineering things such as space flight here. So those 4 basic principles for rocket engines are: the first thing you're going to do is suck. Then you're going to squish, and then you're going to bang, and then you're going to blow. So suck, squish, bang, blow. And this may sound very funny to you, but this is basically breaking down what rockets do to the most basic terms possible. So yeah, laugh it up if you want to about it. But this is actually how it works. So we're going to start off, obviously, with suck. So the first one that we have to do is that we have fuels. Or what, if you're a rocket, or if you're an aerospace engineer, you would call it propellants. You have to have a fuel and you have to have an oxidizer. So fuel is something that burns, and an oxidizer is something that helps that fuel burn more efficiently, or burn at all in some cases. So fuel, you have to find something that's pretty good for that. In rocketry, we tend to prefer liquid fuels. You can also do solid rockets as well, where you actually mix your fuel and oxidizer together and then cast it, like you're making some kind of like you're at a kiln making a beautiful container or vessel, or something to put your flowers in. But you do it with solid rocket propellant instead. You could definitely do that. But for today, we're kind of going to be talking about liquid rocket engines, because that's what most people are familiar with. So what's the suck portion of it? Well, we've got to move that fuel, and we've got to move that oxidizer, and we got to get them together in the engine. So suck comes from the fact that we often have to use pressure for them. There is a way to develop that pressure naturally. It's called autogeneous pressure, and SpaceX is actually working on that with their Starship Super Heavy rocket, where they're basically trying to simplify the idea of delivering the fuel. They still have to use what we have in front of us here with this image, which is a turbo pump. So imagine a pump like you would use for your bicycle, or to pump up the tires of your car. That's usually going to be piston driven. So you're going to have a piston. It's going to open a space that will actually get air in it. You'll shut it off so that air can't escape. You'll open another bit which leads down the line, and then you'll squeeze it, and the air will go down the line into whatever you're adding the air into. Well, imagine instead of a piston, we put a turbine in it. So a big bladed system that spins at ridiculous speeds. And that is a turbo pump. The turbo pumps will spin at unbelievable speeds, moving fuel at unbelievable rates. The Saturn V, the turbo pumps on the Saturn V's first stage, when they're running at full throttle, they're putting the power to spin those turbo pumps is more. It's about 50,000 horsepower more than a Boeing 777 at full throttle, a wide-body airplane at full throttle, just to move the fuel into the engines of the Saturn V. So turbopumps are tremendous amounts of power being used to move those propellants, that fuel and that oxidizer, into the engine with it. So tremendous suction force, vacuum with it there. So that's why suck is our first of the 4 basic principles of rocket engines. And these turbopumps, they have to withstand thousands of PSI. They have to spin at tens, 20, 30,000 RPM. Absolutely ridiculous. They are the bleeding edge of human capability in terms of what we can do. And they have to work. If they don't work, your engine goes boom. And that's bad when that happens. So turbopumps usually are the hardest thing to develop in rocket engines. There's a great book about the history of SpaceX and talking about it. Tom Mueller, who's the head of propulsion, was the head of propulsion at SpaceX until he retired just a handful of, I think it was either 2019 or just last year, he officially retired from SpaceX. There's an in-depth part of that history book about SpaceX that they were just having problem after problem after problem with their turbopumps. So if you're going to start your own aerospace company, get ready to spend a lot of time working on your turbopumps with that there. So just to give you an idea of the amount of fuel that these turbopumps are moving, this is a Saturn V rocket, and it is putting out an engineering measurement that we call 1 standard unit of elephant. And this is how many elephants per second of fuel that a Saturn V is putting out. So a Saturn V's first stage, as you could see right there, was usually putting out anywhere from about 5 to 6 elephants worth of fuel per second. So again, rockets, were kind of talking about the edge of technology of what we're able to do as humans. So there we go. Turbopumps, we're all good. So we got it. We're good with we're good with suck, that first one there. Then we've got squish. So what, pray tell, is squish? Well, to talk about that, we've got to talk about a rocket's combustion chamber. So what is a combustion chamber? It's very descriptive. It's a chamber where the combustion happens. What exactly is that? Because you may have heard of your car's engine before. It's described as an internal combustion engine. Well, it basically means that we're exploding something. So yes, your car's engine runs on contained explosions. And rocket engines are explosions that are contained as well as we can. Sometimes they aren't as well contained, and bad things happen. But we try our best. So the combustion chamber is where the propellant and where the propellants are going to combine and ignite and expand extremely rapidly. And so whether you want to call that a conflagration or a deflagration, supersonic or subsonic, you're welcome to argue until the cows come home on that front. But typically you'll start out at a subsonic speed and speed up to supersonic as you're going out through the nozzle, which is interesting to think about. You actually cause things to light on fire slowly, and then they speed up as they go out the nozzle because of how pressure works. So basically using physics to our own advantage. So inside of the combustion chamber, the turbopumps are dumping, tens, hundreds, thousands of gallons of fuel per second, dumping even more oxidizer in there with it and compressing it all together to thousands of PSI, hundreds of PSI, thousands, just yikes with that there. Yeah, it's a bit that's happening in there, but we really don't technically have ignition yet for most of the types of propellants that we use. So we have to get to bang. So now that we've sucked our fuel through the turbopumps and those turbopumps have dumped them into the combustion chamber where they're squishing together, we have to make them go bang. And how do we do that? Well, this engine is actually a F1 engine that would have been used on a Saturn V. This one's on display at the U.S. Rocket Center, but it was used. You could see inside of that nozzle right there, the scorch marks from it. So what do? We actually have an igniter, and that's the igniter inside of that engine. So this big, massive engine that you and I could literally stand inside of has this itty bitty igniter in there. And that igniter can be a spark, it can be an actual flame, it can be a chemical that's injected. As long as you have a ignition system somewhere in there, it's going to ignite your fuel and an oxidizer mixture, your propellants. And then they are going to energetically react to that, and they're going to expand in size, in volume very rapidly as they heat up. And that is where we come to blow. So blow is basically, we have to make sure that we have a well-shaped nozzle on our rocket so that not only do we get the best efficiency out of it, but we also don't destroy the rocket as the exhaust is coming out. This is a space shuttle main engine on startup right here. This is unbelievable slow motion, 1,000 frames per second right here. And we can actually see the combustion occurring here. And right now it's burning liquid hydrogen, and then liquid oxygen, the oxidizer comes in, and you can see that we go from that orange color of hydrogen burning to that clear, very bright blue of that there. And you saw that it was not a very, what I would call, smooth start. So this is something that we do have to worry about with rocket engines when we start them up. It's usually the hardest thing to do, because as you'll see here, let's take another look at it real quick. You'll see that it's actually a violent process to get that flow, that exhaust flow to smooth out. That engine bell is warping, and that engine bell is made out of 1071 braze welded steel, which, if you know anything about materials, that's some tough stuff. And it's warping like there's nothing to it. That is, it's pretty incredible what we have to do in order to make sure that all of this works correctly. We also have to make sure that our nozzle can withstand the environment that's occurring there. So these exhaust gases are exiting at miles per second, 2 to 3 miles per second, usually. So they're very, very fast. And in addition to that, those exhaust gases are very, very hot. The inside of a space shuttle main engine is at about 5,000 degrees Fahrenheit, so very, very hot. So how, pray tell, are we not melting on the inside of this here? Well, the fuel that the space shuttle used is liquid hydrogen. Liquid hydrogen is very cold. You have to store it at below minus 400 Fahrenheit. So they figured actually that you could run liquid hydrogen through those little pipes that you see on the engine nozzle right there. And there's actually even smaller channels that it runs through. And that would pull the heat away. And it would also heat up the liquid hydrogen and get it ready to dump through the turbo pump into the combustion chamber for the space shuttle's engines. So they ended up actually developing even more efficiency out of the space shuttle's engines by doing that. And we call that regenerative cooling. You don't have to do that for your engines. You could do what's called ablative. So if you've ever seen a rocket engine start up and there's like pieces of it coming off and burning up in the plume, it's probably ablative. That means it just vaporizes the material, and that's how it cools itself. So it's not active, if you will, like the space shuttle is doing here. So yeah, so that's blow with that there. So so to kind of just review them real quick, we suck in fuel and oxidizer from the tanks via a turbo pump. We squish the fuel and oxidizer mix under extreme pressures. We go bang, we bang the mixture by igniting it, kaboom, and then blow the high velocity exhaust in the correct direction. So this is all it takes to make a rocket engine work. It's just a lot more complicated in terms of the machinery that you have to operate with in order to make it work there. But that's really it. That is the principles of a rocket engine broken down about as simply as they can. So hopefully this is a explanation that is good, and feel free to just take this explanation and run with it too. Next time you're at a party, tell your friends all about it. They'll do backflips when they find out about how rocket engines work. Maybe they'll start building some rocket engines in their garage for all we know. But to kind of talk a little bit about the modern groups that are doing rocketry, we can definitely run down the list. So we wanted to talk about present rockets. So now that we're done with the history, now that we're done with how the fundamentals, how do rockets work, let's talk a little bit about who's flying rockets. Excuse me. I was actually going to show you this, which is what happens when all of this all comes together. So, so here we go. This is, of course, the Saturn V. So every time I see a Saturn V launch, I have to remind myself that there's 3 people riding that, and that's the size of a football field. So it's a little big. The interesting quirk about rockets is that 95 to 98% of the weight of a rocket is fuel. That's how much fuel it takes. That's how much energy it takes to put whatever you're putting in space into space. So that means that as you're burning fuel, you're burning weight off of your vehicle. And as you burn weight, that means that you can accelerate faster and faster and faster. So if you're on a rocket, you will accelerate faster and faster and faster because you're burning your fuel. So could you imagine like your car doing that? Like, oh, I'm almost empty in my tank. I've got to be very careful on the throttle with it there. But that's how rockets work. It's not unusual for a rocket in its final stages of burning its first or second stage to actually have to throttle back so that it doesn't break anything it may be carrying or break any of the structure of the rocket as well. So great example of that there with the mighty Saturn V. Has not been a rocket that has topped that since, although in the future, there may very well be that. So to kind of just talk about modern launch systems, SpaceX's Falcon 9, you've probably heard of this one. A lot of space people have. If you haven't, now you know. Able to carry cargo and crew and reusable, a partially reusable orbital launch system. The first stage comes back either on a drone ship out in the ocean or at a landing pad near where it was launched from in Florida or here at Vandenberg Space Force Base in California. Yeah, just a fantastic rocket. SpaceX really did change the game in making things cheaper than was expected for that there. So we're kind of watching everybody. I don't want to say everybody play catch up, but yeah, everybody's making a move in response now to what SpaceX has brought to the spaceflight industry. Some other rockets that are still flying, one of SpaceX's main competitors, and I guess you could also say SpaceX is a main competitor of these folks too. United Launch Alliance, ULA, their Delta IV Heavy rocket is still flying. It only has 3 flights left. It is a massive rocket. So much like Falcon Heavy, where you strap 3 Falcon 9s next to each other, the same thing with Delta IV Heavy. They're no longer flying what we call the single sticks, which are just the core in the middle there by itself. So they're only flying heavies from here on out, but there is one more Delta IV Heavy. It's going to fly out of Vandenberg sometime next year. So if you're in the California area and you've always wanted to see a rocket launch, Vandenberg Space Force Base, you can go watch rocket launches there, just as close as Kennedy or the Cape, and it's the same rockets that they launch from there as well, so just as big. And it's pretty spectacular. Gotta recommend you go see them if you can. Also from United Launch Alliance, their Atlas V rocket is still flying as well. The Delta IV Heavy that I showed you earlier, this one here is pretty much carries payload only, but the Atlas V is crew rated, so that means you can stick a vehicle on top of it. And Boeing, their Starliner, which is their commercial crew vehicle, will fly on the Atlas V, as will proposals. There's a company called Sierra Nevada Corporation developing a space plane called Dream Chaser. They might put crew on, and if they do, it will probably fly on the Atlas V. Kenneth, you're asking, do rockets use as much fuel to return as it does to take off? They actually don't. So when a Falcon 9's first stage is on return, it is significantly lighter, less weight than it was at liftoff. So they don't have to keep much fuel on board. There's no official word from SpaceX as to how much fuel they actually use. You could definitely calculate it in terms of math and other things like that, and I'm pretty sure other people do. But I would venture to say that probably 10 to 15% of the total amount of fuel in a SpaceX's stage one for their Falcon 9 would be needed for return, something like that. So it's very small. And then also SpaceX did something interesting with their Falcon 9, which is that they improved it. They kept doing things to increase the efficiency and the ability to carry fuel and things like that, which ended up basically making that 10 to 15% a moot point. So not much loss of performance with it there. But I mean, it does knock performance. You can fly a Falcon 9 expendable and carry more payload into space, but also SpaceX will charge you more for that as well. And so far, most people are not really needing to fly expendable Falcon 9s because SpaceX has just engineered the Falcon 9 so well that it's pretty much overpowered for most things, intentionally overpowered to make sure that it has enough fuel and oxidizer to land. So great question there, Kenneth. We also have other companies as well. Northrop Grumman with their Minotaur family of vehicles. These are basically the solid motors of old ICBMs, like Peacekeeper missiles and other things like that, repurposed for peaceful purposes to launch with that there. They also have their Antares rocket, which is used to loft payload for the commercial cargo program. Their Cygnus vehicle primarily has been the only thing that has flown on Antares. And they're still flying them as they continue on with that there. Antares is a very interesting rocket. The first stage is liquid fueled. That uses refined kerosene, what we call RP1, and liquid oxygen. So take oxygen, dip it down to below minus 270 Fahrenheit, and yowza, it's a liquid. But the second stage is a solid. So it's two different kinds of propellants there, and it works just fine, but just an interesting design choice from them there. And then Northrop Grumman also has the Pegasus XL, which is a air-launched rocket, one of the first commercial air-launched rockets. This is an all-solid vehicle, again, using leftover ICBM motors and other combinations thereof. And they actually will fly up to about 40,000 feet and drop it from a L-1011, old Lockheed TriStar that they still use to carry these rockets around with it there. And you'll notice that on here, it does say Orbital ATK, and that's because Northrop Grumman did buy Orbital ATK and kind of made them a part of their own company, took them over with that there. We also have Rocket Lab, a little local, a little. No, they're a pretty local and growing company that has their Electron rocket. They do launch it out of New Zealand, but they are considered an American company because they want to make sure they get American contracts from the United States government, because those are pretty hefty and you like money in aerospace. As the old joke goes, you want to know how to be a millionaire in spaceflight? Start out as a billionaire. So companies succeeding is a pretty rare thing, actually. But Rocket Lab is thriving pretty good with what they've got. They've also got some other cool things where their upper stage of their rocket you can actually build it in-house with Rocket Lab to be your satellite. Just some really cool stuff that Rocket Lab has done. Basically, why go to another company when you can buy everything all in one place? That's what Rocket Lab has done. So pretty cool. We've also got Virgin Orbit with their Launcher One vehicle. Yes, that is a big honking rocket being dropped off of a 747 there. So yeah, from the Virgin company. And that was the first liquid-fueled air-launched rocket. So they use that RP1 liquid oxygen mixture of fuel and propellant, or fuel and oxidizer for their propellants. And they actually just had a launch just a couple of days ago, and it was successful. Their second successful one in a row. So congrats, Virgin Orbit. We actually do a lot of work with Virgin Orbit here at the Space Center. Really, really fun to help out the community with them. Also, Arianespace, their Ariane V, a very big rocket, very near heavy lift with that there. And later this year, the Ariane V will be launching the James Webb Space Telescope. So if you've been following that saga for the decades that it's been going on, the time is almost upon us for it to launch. And then 1 month of terrifying origami as the Space Telescope unfolds over 30 days. So that will be fun. Maybe we'll talk about that in a Space Center Live as we get a little closer towards the launch date later this year. So stay tuned for that. But Arianespace, a consortium of countries from Europe, all just basically going all in on making a launch vehicle that they can use, so that way they don't have to go to Russia or the Americans to do that. They have their own rocket, and great. The more rockets, the better. SKB Progress, Russian company, builds the Soyuz family of launch vehicles, as we talked about earlier, the descendants of the Soviet R-7 ballistic missile from the 50s, still flying today. Incredibly adaptable design with what they were able to do with the Soyuz, and just really cool overall to see those flying. And actually, one just launched a Progress cargo vehicle to the International Space Station a few days ago. Coming up, Khrushchev with their Proton rocket. They are actually getting ready to launch a Proton rocket with a new module for the International Space Station for the Russian segment. And that's going to be pretty cool. Proton is a heavy lift vehicle, so it's pretty good size. You can see some of the people standing towards the bottom of it there. So very big rocket with that. So good at heavy lifting. The Chinese National Space Administration has an entire family of rockets, Long March, with a letter to designate them there. This is their biggest rocket that they have so far, the Long March 5. That's the one that launched their cores, or the core for their space station, Tianhe 1, which you may have heard of a few weeks ago, because people were saying the upper stage is going to crash somewhere on Earth. And, think about how much ocean there is on Earth, and then think about where people live and how little land that actually covers. So yeah, but anyways, they're actually developing more rockets. They have an entire line of rockets. I could literally do an entire Space Center Live just about China's space program, because it's fascinating history of what they have there. And they're developing some even bigger rockets than the Long March 5 right here. Japan, the Japanese Aerospace Exploration Agency, working with Mitsubishi Heavy Industries, has a rocket called the H-2B that they still use. They've used it to launch JAXA science probes into Earth orbit, and also on interplanetary missions, and ComSats as well with that there. And they have, I think, one of the most beautiful launch sites in the world, the Takashima Space Center in southern Japan. And I would actually like to go see it if I ever go to Japan one day. It's gorgeous down there. That's why I could not crop this image. It's just too beautiful to do that. It would be a disservice to that space center because of how beautiful it is. Also, the India Space Research Organization, ISRO, they have their polar satellite launch vehicle. So they use this one to launch vehicles into polar orbit or smaller payloads to equatorial or geosynchronous orbits. So this is one they use. They also do have a geosynchronous satellite launch vehicle, the Mark III of that as well, a much heavier lift vehicle with that there. And yeah, pretty cool. India is actually working on getting a human space program going, and I'm very excited to see what they bring to the table. And this here, the geosynchronous launch vehicle is likely to be the main launch vehicle to launch astronauts from India into space. So very excited to see what they do with that. And then we can talk about sort of the upcoming rockets that we have on the horizon, Khrushchev with the Angara family. So once again, going back to Russia, the Soyuz and Proton is kind of old and outdated, so they're upgrading it to the Angara rockets. These are going to be modular, they're configurable, you can add boosters to them. Like you can see here, there's 4 liquid-fueled boosters on this Angara here, and kind of, plug and play, whatever you need to do with that there. The Arianespace is responding to SpaceX dropping the costs of spaceflight by going to the Ariane 6, basically a bigger Ariane 5 with more solid rocket motors on it, and able to lift more at a lower cost. They are talking about putting reusability into it, but down the line. So take that as you will. A lot of people would say that the future is reusable rockets. If you're not making your rocket reusable, you will go the way of the dinosaur in aerospace. But I mean, we'll see. We could do a whole other Space Center Live about that too. So United Launch Alliance, they're working on their Vulcan Centaur rocket. which again, another sort of plug and play, cost effectiveness and simplicity with that there. And they are working on a reusability system called SMART, S-M-A-R-T. Forgot what the acronym stands for, but basically the area where the engine is at detaches, deploys a heat shield, and then it enters the atmosphere, and the engines are picked up under parachute by either an airplane or a really heavy lift helicopter, and the engines get reused. Because as you can imagine, we talked about rocket engines today. They're very complicated, which means they are very expensive. So United Launch Alliance's idea is that the engines, reuse those, and you'll handle most of the costs. But United Launch Alliance has also dropped their prices significantly as well through a lot of reorganization and things. So we'll see. And Vulcan Centaur should be launching sometime in the next 12 months. So we're pretty excited about that. And then Blue Origin, they have New Glenn. Don't let this little image of it or graphic of it fool you. It is a gigantic rocket. Over 220 feet tall. It's big, and it will be reusable. They're doing reusability right out of the gate for that there. So heavy lift rocket, and we'll see what they do. I believe 2023 is now the time frame in which they're looking at flying that. And then, of course, we can't talk about the future of rockets without talking about SpaceX with their Starship Super Heavy vehicles that they're testing out in the view of the public. I guess this is what it was like to watch NASA in the 50s and 60s as they were doing their crew programs to send people to space. So we get to watch them blow things up. But hey, if you're not breaking stuff, you're not testing. As the old adage goes in engineering with that there. Starship Super Heavy would, once it flies, it will be the biggest rocket that has ever flown, most payload ever put into orbit. Yeah, just, you want to talk about superlatives. Yeah, and I believe it will also be the first fully reusable rocket as well. The space shuttle could reuse its SRBs, but the external tank, the orange tank that fuels the main engines, that would be jettisoned and burned up in the atmosphere. Starship Super Heavy, the booster will come back and land either at the landing site or on a drone ship, out in the ocean, just like a Falcon 9 Stage 1 does. And then Starship, the actual spaceship itself, is designed to be reusable as well. So this would be a fully reusable launch system, which once that's implemented, that will certainly bring down the costs. So overall, that is what we got today for Space Center Live. If there are any questions, we can definitely take them right now. While I'm stalling for time to see if there are any questions here, because we answer your questions live on the air, and we've had a couple. Thank you all for who've asked the questions today. Just to let you know, the Columbia Memorial Space Center will be reopening July 9th. So right now we're looking at reopening on July 9th. And don't know all the details on that. Check out our website, columbiaspacescience.org, with that, and get up to speed on that there. But July 9th, we are reopening to the public. I do believe we are going to be limited, and I do believe masks are still a thing. I do think we have someone who works at the center watching as well, who can maybe say in the comments what's up, and I can repeat that back so folks who are watching on demand can catch that as well. So Kenneth, you asked a really good question, which is, are there any innovations happening with the fuels? So actually, at the moment, not really. Nobody's really looking at doing things with the fuels, simply because we found really good combinations that aren't too toxic. Always like to put it that way, aren't too toxic, and are good efficiencies, or good efficiency for what we get. Really, the biggest innovation that's happened in fuel recently was something that SpaceX did called propellant densification. So basically, SpaceX chills down their liquid oxygen and their RP1 to colder than it actually needs to be. And when you chill something cold, you can increase the density of it. So if you were to take your liquid oxygen and make it, like, say, 40 degrees Fahrenheit colder than where you would normally have it at when you're putting it in a rocket, you can actually fit more liquid oxygen. You can increase the density inside the same fuel tank. Same thing with your kerosene, your RP1, your rocket propellant one. You make it cold. You don't freeze it, but you make it cold. And you can fit more RP1, the highly refined kerosene, into your fuel tank there. And that's actually what SpaceX did with the Falcon 9. And that's why they were able to, that's why Falcon 9 is able to have such high performance, even when it has to still land or have propellants to land either out in the ocean or back at the landing zone near the launch pad. So great question there, Kenneth. Also, just a little thing in case you didn't know about this, Boeing did help do a lot of research for that. And the primary base for that research was here in Downey at our facility, our former industrial facility that was here. So I am sitting where the things that made SpaceX work were initially thought of back in the 1990s, or at least thought of seriously back in the 1990s. So, which is pretty cool if you ask me. So with that, so very cool. All right. And we could kind of hang tight a little more for some more, any more questions that maybe kind of like maybe another minute or two. We do not have a subject nor date for our next Space Center Live, but we'll definitely put that out on social media pretty quick. So don't worry, we'll let you know. So stay tuned to our Twitter account, our Instagram account, and our Facebook if you haven't got us already on there. Columbia Space is where we're at on all three of those. So make sure to check us out with that. And I do believe because we are not seeing any questions come in, we're just going to go ahead and wrap this up. So thank you all of you who tuned in today. Great to have you watching us here at the Space Center for Space Center Live, and have a good one to all of you. Have a very nice weekend. Stay safe and enjoy your 4th of July.